Hey y'all, it's your personal math teacher, Mr. Boyden, back at it again, and today I'm going to be showing you how to calculate a confidence interval for a proportion. Let's get started. Last class we talked about how a confidence interval is always the point estimate plus or minus the margin of error. Today we're going to learn what the margin of error is for a proportion. It's two components. It's the critical value, which we'll learn about in just a minute, and the standard deviation of the statistic, and they are multiplied there, right? Okay. A critical value, an easy way is of thinking of it like a z-score, and specifically on the standard normal curve. So to calculate it, let's say we were going to do a 90% confidence interval, and we wanted to know what is the critical value. Well, what we would do is we would consider the standard normal curve, and we would want the middle region to have an area of 0.9, okay, or 90%. If 90% is there, that means there's 5% on either side. And so when we go to type this in, because really what we want to know, this is negative z star right here, which is the critical value. Critical value is referred to as z star. Okay, and we have positive z star over here. So we can find either of those. They are symmetrical about the mean of 0 on this. That's always true. Okay, so I'm not going off script there with that. But then all we would do is we would go to inverse norm in the calculator, and we would fill in 0.05 for that tail area on the left, and then the mean of 0 and the standard deviation of 1 will autofill for us. And in this case, what we get when we type that in is it's going to say negative 1.64. We always consider z star, we take the positive version of it. Okay, so in this case, the critical value for a 90% confidence interval is 1.64. Okay, and that's all it is. We're going to do another example here in just a minute, but that's how we calculate them. Okay, so here's our definition for how to calculate a one sample z interval and that is a confidence interval, by the way. Don't get caught up in the language on this. This is how we do a confidence interval for a proportion. It's just that it's called a one sample z interval. Okay, and so guys, here it is down here. This is exactly what we learned just earlier now and in the last class. It's the statistic, which is p hat, plus or minus z star. That's the critical value, which we just learned how to calculate. And then we said it would be multiplied by the standard deviation of the sampling distribution. Well, remember that formula from early in our learning, okay, or a little bit earlier in our learning. Okay, p hat times 1 minus p hat over n. Don't forget your square root on the top of it. Okay. Right below here, I put that general form for a confidence interval just to show you, yep, that's p hat. This thing over here, including z star, that's how we calculate the margin of error. Okay. Now what about conditions? So look at what we have going on here. First of all, when we calculate our z star, our critical value, we used a normal distribution. And so automatically we should look at that and say, well, wait a minute, how do we know if it's normal or not? Well, we might know with the large counts condition. Okay, so that's one thing that we need to think about. The other one is, do you remember that for this formula, we had to make an assumption of independence? And in order to do that, we had to meet the 10% condition. Okay, now there's actually another one that we have to have as well. So let's go look at those right now. In order to construct a confidence interval for a proportion, we have to meet these three conditions first. Okay, and they are bolded here. The first one is we need to have random study design. The second one, since we're referring to a normal distribution, we need to verify approximate normality of the sampling distribution, and we can do that with the large counts condition. And then finally, we need to verify that the 10% condition is met. Now guys, if you want to pause here, I did put the equations on here again and the formulas for each of these. They are here for you. Okay, so if you want to pause and if you need to be reminded of those, or if that's new to you, that's totally fine. Let's try this question. Sleep Awareness Week begins in the spring with the release of the National Sleep Foundation's annual poll of U.S. sleep habits. And it ends with the beginning of daylight savings time when most people lose an hour of sleep, which actually happened last night as I recorded this video, oddly enough. In the Foundation's random sample of 1,029 U.S. adults, 48% of them reported they often or always got enough sleep during the last 7 nights. And we're going to run through a series of questions on this scenario. First of all, we want to identify the parameter of interest. Okay, to identify the parameter, remember we're talking about the population. Let's first figure out what's the population. Okay, they said they did a poll of US sleep habits. Most people lose an hour of sleep. The population is US adults. Okay, they did a sample from US adults, and so that's who the population is. Now, what did we measure? They measured people who report often or always got enough sleep in the last 7 nights. So what is our parameter of interest? The percentage of all US adults who would report often or always when asked if they got enough sleep in the last 7 nights. Based on the way they designed this sample, that's what they're trying to predict, or that's what they're trying to make an estimate of. And remember, confidence intervals are an interval estimate. Now we're asked to check to see if the conditions for constructing a confidence interval for P are met. Okay, let's run through the 3 conditions. The first one is randomness. Okay, did we do that? Up here they said a random sample. So all I'm going to do for this is I'm going to put that they had the phrase, they did a random sample. Okay, so check. I've checked that condition. Number 2, let's do the 10% condition next. The 10% condition, the sample size was 1,029. And so all I'm going to say here is, because we don't know what the population of US adults is, but I feel pretty confident that if we only asked 1,029 people, we've asked less than 10%. So we're just going to demonstrate that we thought about this. 1,029 is less than 10% of US adults. And that's totally acceptable for an AP exam, y'all. You need to demonstrate that you understand what the 10% condition is, that you thought about it, and this situation likely meets it. On the 10% condition, there are times like this when you actually can't use the formula because we don't know what the population size is. Okay, and the third one is we're going to check the large counts condition, LCC. Okay, and so that would look like 0.48, that's our sample proportion, times 1,029, that should be greater than or equal to 10. It obviously is, just at a glance, that's in the neighborhood of 500 being bigger than 10. And we need the complementary proportion, 0.52, even bigger, to be greater when multiplied by 1,029. And it appears that it is. Okay, so that's the third condition. Check, check, check. I want to encourage you on exams to show those 3 checks because that's what graders are going to be looking for. Okay, so put all 3 checks in there. Now they want us to find the critical value for a 98% confidence interval. I really want to encourage you to do this calculation on your own first and then continue watching the video. So I want to encourage you to pause, use the notes and the learning we already did to practice this on your own right now. Okay, so I always draw the picture on these. Let me zoom in a little bit so you can see the picture that I draw. I always draw the picture, so normal curve. Center area is 98% or 0.98, which means the tail areas are 1% or 0.01. That way they add up to 100. Inverse norm, and that inverse norm is going to have an area that stops at 0.01, mean of, 0, sorry, and a standard deviation of 1. Notice those values are probably already filled in your calculator. And when we do that, we should get a Z star value. And guys, please make sure you connect in some way for yourself that a critical value and Z star for a proportion, those are the same thing. Okay, that value is 2.33. Okay, they then ask us to calculate the interval. Right now, I'm going to show you 2 different ways to do this. So I'm going to show you how to do it by hand, and I'm also going to show you how to do it with technology. Okay, so let's start out by doing it by hand. Okay, we had that formula from up above, and that formula was p hat plus or minus z star times the square root of p hat times 1 minus p hat over n. And so all we're going to do right here is we're just going to start plugging in those values. We were told that p hat is 0.48 and that the sample size is 1,029, and we now know the sample size, so we can plug those in right now. So 0.48 plus or minus the z star we just calculated, 2.33, times the square root of 0.48 times its complementary probability, 1 minus that, which is 0.52, divided by 1,029. And so one way of generating the confidence interval is if we type all of this in our calculator. You type it once with a plus, then you go back, type it again with a minus. However, I want to show you another way. To get a confidence interval in the TI Inspire, we need to go to any calculate page. And then remember, pretty much anything good in this calculator happens in the menu. So we're going to go menu, we're going to go into the statistics menu, and notice down there, number 6, the submenu is confidence intervals. And so that's pretty straightforward. Here is where there's 8 different types of confidence intervals though, and so this can get a little bit treacherous. We're talking about proportions, that's what that prop is right here. We only recorded 1 proportion, not 2 proportions, and so number 5 is the one that I'm going to choose. Now when I get into here, some of this information I know right away, like the sample size was 1029, and the confidence level was 98%. But successes is a little different. So the number I need to get here, remember 48% of the people answered often or always. So what I need is 48% multiplied by 1029. The problem is the calculator doesn't want to do math in this little box, and so I'm going to grab a little calculator in my hands, where I'm sitting right now, and type in 0.48 times 1029, and I got a number that rounds very closely to 494. Whoops, sorry, 494. And so that's all the information that I need. So let's go back over here, and now right here, the calculator has just given me my confidence interval when it says lower and upper. So they've shown me down here what the margin of error was, and we would get something very similar if we calculated it by hand. And I'm going to round these, looks like 0.443 and 0.516. Now we need to interpret the interval in context. This is one of those canned responses, so pause the video and try this one, and then see if you agree with my response. Here's my interpretation. We are 98% certain that the interval from 0.443 to 0.516 captures the true proportion of US adults who would answer often or always when asked if they got enough sleep in the last 7 nights. If you're one of my students, always give the full context when you answer an interpretation question like this. Sometimes in my experience, students will say like, we're 98% certain that the interval from 0.443 to 0.516 captures the true proportion. That's not good enough. Both on my exam and on the AP exam, you're going to get marked down for that. Because this isn't a math question, this is a contextual question. Okay, it's talking specifically about US adults reporting on a sleep survey. And that's part of why in number 1, they asked us to identify the parameter. And notice how thorough I was with my answer there. I'm trying to model for you keeping all of the information of the context for your answers. So do a double check right now. Compare what I wrote here to what you wrote, and make sure you have all of that information in your sentence as well. Okay, guys, that's the basics of how to calculate a confidence interval, okay, for a proportion. There is one other thing that comes up, and that is regarding sample size for a desired margin of error. Okay, so what we've learned so far today is that we now know how to calculate the margin of error, and that's shown up there right at the top of the screen. And sometimes we know in advance what margin of error we want. So there's an example here. If we're doing a poll on elections and we want the margin of error to be 2 percentage points, should say 2 percentage points or less, on a 95% confidence interval, if that's the case, we actually can determine the sample size we need in order to guarantee we achieve this margin of error or better. And so that's what we're going to figure out right now. Now you might be wondering why that's important, like real world wise. Well, because a lot of times the companies who are doing these polls, they're hired to do so. And if they go out and they accidentally get a poll that has a really big margin of error, and they have this big wide confidence interval, that's not very usable by the campaign or by whatever group wanted that confidence interval. And so sometimes they'll do this calculation in advance so they get a big enough sample size to guarantee that they have an acceptable margin of error. Okay, so here's how we do that. The way I start it is like this. I say I want the margin of error to be less than or equal to 0.02. That's the 2 percentage points. Next, I'm going to remember that the margin of error is z star, times the square root of p hat times 1 minus p hat over n. And my square root should have gone down a little farther. Sorry about that. Please be a little more particular than I was there, a little more precise. Okay, and I'm kind of just going step by step here. Now I need to start filling in those values. And so one of the things that I'm noticing already is I have not yet calculated a z-star value for a 95% confidence interval. So normal curve, 95% is in the middle, which means 2.5% is on either side. Once again, same calculation, inverse norm, 0.025 is the area, 1 and 0. And when we type that in, we get something that rounds to, it's about 1.96. Okay, so for now we know the critical value for a 95% confidence interval. We can start filling that in over here. So 1.96 times the square root of, do I know what p hat is? All right, this is tricky. We don't know what p hat is because we haven't done the survey yet. We'll talk about that in just a second. Down here, we'll just put it over n. We recognize that's what we're solving for, but we need to talk about p hat for just a minute. What's going on with p hat? Well, with p hat, we're going to use 0.05, and here's why. We know that these two values up here, p hat and 1 minus p hat, those two values have to add up to 1. And we're going to do what's called a conservative estimate. And you'll see that a lot of times written in questions. A conservative estimate. Okay, so what that basically does is if I choose 0.5 times 0.5, those two values together, multiplied together, come out to be 0.25. Well, what's the significance of that? Well, let's say that instead I had guessed 0.4 times 0.6. Those two numbers also add up to 1. So 0.4 times 0.6, that comes out to 0.24. Doesn't seem very interesting yet. Let me do one more. What if I had chosen 0.3 and 0.7? Multiply those together, that comes out to be 0.21. Okay? It turns out that by choosing 0.5 for p hat, I get the largest value right here, which is the value that we're about to put up here in the numerator. And what we want to do, we want to make that value as big as possible because that represents basically our worst case scenario for making it a large margin of error because it's in the numerator. And so we're going to just make up a value of p hat that represents the largest possible margin of error. And so 0.5 times 0.5, and unless we're told otherwise, that's always what we're going to use. Okay, if they tell us to use something else, fine. But if they don't tell us, this is what we'll use. So from this point, we get to do a little bit of algebra. To do this, let's divide both sides by 1.96 to get rid of the 1.96. Let's square both sides. That's a decimal, by the way, to get rid of that radical. I'm going to rewrite what we have now. That simplifies to 0.25 over n is less than or equal to 0.02 over 1.96 quantity squared. And then we're going to do two moves in one here. The first thing we're going to do is we're going to multiply both sides by n so that n's not in the denominator. And then in the same move, we're going to divide down that entire quantity on the right side. So what we end up with is 0.25 divided by 0.02 over 1.96 quantity squared is less than or equal to n. And so from here, we're going to go type that in our calculator. When I type that in, I get a decimal that's just a little bit over 2,400. Now what we're trying to get here is the minimum sample size needed to guarantee that our margin of error will be less than or equal to 2%. And so what I'm going to do is no matter what that number is, I'm always going to round up to the nearest whole, because by rounding up, we remember bigger sample size starts to get more specific with our results. I'm always going to round up to the nearest whole, and so that's going to land on that my sample size needs to be at least 2,401. By doing so, no matter how the people answer the poll questions, no matter who they're going to vote for, I'm guaranteed that I'm going to get a margin of error of 2% or less. Okay, let's do one final question. A company has received complaints, oh no, about its customer service. The managers intend to hire a consultant to carry out a survey of customers. See, they're hiring someone just like we talked about before. Before contacting the consultant, the company president wants some idea of the sample size that she'll be required to pay for. One value of interest is the proportion, P, of customers who are satisfied with the company's customer service. She decides that she wants the estimate to be within 3 percentage points at a 95% confidence level. So we have a few questions here. Using a conservative estimate for p hat, how large a sample is needed? Okay, well that's the same thing that we answered just a few minutes ago. Okay, so let's fill this in. When we talk about a 95% confidence interval, it's that same value again for the critical value of 1.96. So 1.96 square root of, okay, n's on the denominator, 0.5 times 0.5 in the numerator. But this time the only difference is we want it to be less than or equal to 0.03. Now notice how that's the exact same setup we had in the previous question. Okay, that means all the steps are going to be the same. Okay, so in fact we can do all those steps in one maneuver right now. Okay, 0.25 over 0.03 over 1.96 quantity squared is less than or equal to n. And guys, if you're like, wait, that went really fast, what are you doing? That's so crazy. I want you to reverse the video for a minute. I want you to go back up to here and notice that if you do the exact same steps that I did up here, that's what you'll get. Okay, that's one thing. This question looks hard, but every type of question like this goes through the exact same steps. Okay, and so when we type that in, what we're going to find out is that we need a sample size of at least 1068. Now think about that. If you have a bigger margin for error, you don't need as large a sample size. Okay, that kind of makes sense. Okay, what about part B? In part B, in the prior year's survey, 80% of customers surveyed said they were satisfied. Using this value as a guess for p hat, find the sample size needed for a margin of error of at most 3 percentage points with 95% confidence. Okay, so this is something that companies or survey or polling companies will sometimes do. If you already feel like you have a good idea of how people will answer, you can make a sample size estimate or sample size needed estimate based on that. So that's what we're going to do right now. So it's going to be very similar to what we had up here. It's still the same confidence level, so 1.96 for Z star. The difference is going to be this time, we're not going to do 0.5 and 0.5, we're going to do 0.8 and 0.2. And we still want it to be less than or equal to 0.03. So how is that going to change our final outcome? We're still going to go through all the same steps as we would have before to solve this. The only difference is that instead of having 0.55 and 0.55 multiply out to be 0.25, this time we're going to multiply 0.8 and 0.2 down here, and we're going to get, well, a different number. So 0.2 times 0.8, that's 0.16. And so that when we do the algebra on this one, we're going to get 0.16 divided by 0.03 over 1.96 quantity squared is less than or equal to n. And same deal, y'all. We're just going to type that in our calculator and see what we get. Okay, and so we get a value, remember to round it up, and this time we need our sample size to be at least 683. Now, this is part of what I mean when I said earlier that using this value right here, 0.5 for p hat, that's a conservative estimate. It's going to lead us to a sample size that is biased toward being too large. And that's a good thing, because in terms of making sure we meet our goal for margin of error, having a sample size that's too big will only help us. Cost money, but it's going to help us for margin of error. Okay, versus if we use a predicted value like we did in the second one, we're going to get a smaller margin of error, or excuse me, a smaller sample size. The risk here is, what if the proportion of satisfied customers has changed in the last year? It's possible that we could end up with a larger margin of error now because we did not use the conservative estimate. Okay, last question. What if the company president demanded a 99% confidence interval? Would that be a smaller or larger sample size, assuming that everything else remained the same? What do you think? To understand this more easily, let's consider how that would change down here with our equation. It would no longer be 1.96. With a 99% confidence interval, if that's 99 in the middle, 0.99, then we have only a 0.5%, 0.005 available over here. So that's going to lead us to a different value for z star, for the critical value. Okay, and it turns out that value is going to be 2.576. Let's consider how the rest of this equation changes. Well, it really doesn't. And so we get still 0.8 times 0.2 over n less than or equal to 0.03. Okay, and so guys, we can still, in fact, why don't we actually solve this out and see what this comes out to? We get 0.16 over 0.03 over 2.576 quantity squared less than or equal to n. And when we type that in, we get a decimal that when rounded up is 1,180. Okay. In order to keep our margin of error at 0.03, because we can't change that, we would have to get a larger sample size. Because basically when we say our margin of error is 0.03, we're saying that the interval cannot get wider or narrower. So we want the same width of interval, but with higher confidence. In order to get a higher level of confidence, we're going to need a larger sample size. Now y'all, if you're feeling like, oh geez, that algebra jumping from here to there was really, really hard for me, I want you to go back to the section in the video where we went through this example and went through the steps. Okay. In AP, we're talking about a timed exam and we want to be really efficient. Now, I want you to get it down, of course, but I don't want you to be fighting with going through every single step and showing every single step every single time necessarily, unless you feel like you really need that. Okay, so study that one again, and then maybe after you see that, then try these examples to make sure you feel really confident, haha, pun intended, in what you're doing. People, that's all for today. We've talked about how to calculate a confidence interval for a proportion, and how to find the sample size needed for a given margin of error. I hope this has been helpful, and I'll see you next time.